Each of the speakers will give themselves a very brief introduction.
Also haven't heard what I have to say yet. So that's good. Hi, everyone. Good morning. The symposium is already off to a great start. Lots of insights from even just the previous session. I know I was taking notes. So like Sean said, I am Angel, and I am a PhD candidate in chemical engineering, working with Drs. Heather McLean and Brad Seville at the University of Toronto. And this morning, I've been tasked, like Sean said, with setting the context for bioenergy with carbon capture and storage, and I will call it BECCS during this presentation. And I'm actually going to get us started off with a question to think about. Let's just make sure this is working. Awesome. So what if we could harness our biomass for the dual impact of clean energy generation as well as climate action? So we know that Canada has vast biomass resources, from forestry to agricultural biomass, etc. But what if we could actually take this single resource and use it for this dual impact of both being able to address the climate challenge as well as deliver clean energy? Right? This seems really, really promising, and this is the potential that BECCS could deliver if deployed sustainably. So our research group has been working to answer questions on how exactly BECCS can be sustainably deployed on a large scale in Canada. But before I get into our work, let's backtrack a little bit. What exactly is BECCS? So some of us may be familiar, others not, so that's why it's really important for us to set the context before diving deeper into the session. But as the name implies, bioenergy with carbon capture and storage is a promising technology that involves capturing the carbon dioxide that's released when biomass is converted into energy. So the BECCS process begins as biomass is grown or cultivated. And I think we all know that in order for this to happen, biomass absorbs carbon dioxide from the atmosphere and stores it as carbon. Now, when the biomass is processed and converted into energy, for example, let's take a combustion process where biomass is burned to generate heat or electricity. The carbon that was stored in the biomass gets released back into the atmosphere as CO2. However, if we could capture that carbon and permanently store it, either underground or in long-lived products, then the process could potentially deliver negative emissions. So this is essentially a net removal of CO2 or carbon dioxide from the atmosphere, the climate action piece, while also generating renewable energy to supply our sectors in the industry, heating, etc. Now, there isn't one single BECCS technology, but there's different pathways depending on the feedstocks and the conversion routes. So for example, we have biomass such as oil crops or lignocellulosic, agricultural biomass, etc. And these can be used as feedstock in different bioconversion processes. So for example, thermochemical processes like combustion, which I mentioned earlier, or gasification, or even biological routes like fermentation. I think fermentation to ethanol was mentioned in the previous session. And these processes have a variety of energy products, with broad categories being heat, power, and transportation fuels. So the bioenergy piece in BECCS has the potential to generate these energy sources from renewable biomass. And when we add the CCS piece, or the carbon capture and storage, then this can potentially make the process carbon negative. So now we know what BECCS is and how the technology works, but why is it relevant? Why is this important? BECCS is actually projected to play a major role in Canada's carbon management strategy, which includes net zero electricity by 2035. So this figure here is from the latest Energy Futures report, and Canada projects that through BECCS, electricity can actually be net zero by 2035. So that's close to the start of that green line over there. And this is despite bioenergy making up only about 4% of total generation. So that's a big impact. And it's actually projected that by 2050, BECCS could deliver about 40 megatons of CO2 removal. To put that in context, that's nearly 75% of Canada's GHG emissions from 2020. So that's big. And then beyond Canada, BECCS is included in nearly all climate scenarios and pathways as a critical technology that's needed to move us forward in our net zero goals, both in the near term and the long term. So in this figure here, what you're seeing, if I can get this to work, are different climate models, and the numbers represent a percentage of 2018 global net zero emissions that these models are estimating that BECCS could remove by 2050. And when we look at all the models, the range is between 3 to 31% of 2018's total GHG emissions. And this amounts to up to 15 gigatons of carbon dioxide removed annually by 2050. Now, the variation in these models is due to different feedstocks and technical assumptions that they're making. But just looking at the magnitude of CO2 removal here, it's pretty clear that BECCS has great potential in inching us closer to our climate goals. But despite this potential, there's still lots of questions that remain. For example, exactly how much biomass is available for BECCS? And how can we harness this biomass sustainably? What are the resource requirements in terms of energy, land, water use that are needed to be able to deploy BECCS on a meaningful scale? And what even is a meaningful scale for BECCS deployment? How much CDR can we actually get from BECCS, and at what cost, whether it's economic, environmental, or even social costs like we just heard about from the previous session? So these are really important and crucial questions that need to be answered in order to guide us forward in terms of sustainably deploying BECCS. And one of the challenges with these questions is that there's not a one-size-fits-all answer, right? The answer is going to vary by region. For example, things like resource availability, or even the policy landscape like we were just talking about, these are going to vary depending on the region. And in Canada specifically, there's still lots of gaps in our understanding of what it's going to take to sustainably deploy BECCS on a large scale. So like I started off, our research group has been working to answer these questions, specifically as it pertains to the Canadian context, in order to provide novel and relevant insights to advance Canada's climate goals via BECCS. So in the little time I have left, I'm going to share with you some of our recent work and preliminary findings. First, we set out to quantify the availability of biomass resources in Canada. And it's been a challenging expedition because there isn't a single national database that has all the biomass resources that we have, where they're located, the quantities, et cetera, although that would have been very convenient. So we started off with just quantifying residual biomass resources, so that's waste biomass. And Deanna, who's a student in our group, has been working to quantify the agricultural biomass resources that we have, specifically in the Canadian prairies. So far, the focus has been on wheat, barley, and oat straw, as these are some of the most abundant agricultural residues that we have. And she's been able to generate some maps. So this one shows the spatial distribution of the crop residues in the Canadian prairies. And it's a township level estimation that basically factors in constraints like the residue availability, as well as other technical constraints like competing uses. And Emily, who's a postdoc in our group, has been working on the forestry side, again, to estimate the availability of forestry residues for BECCS, also using a geospatial analysis approach. And we can see here from the map, if you look at this orange, dark red region, that BC is kind of leading in terms of the forestry residue density there. Now, there's also no comprehensive study on exactly how much CO2 can be removed from BECCS in Canada. So that's what I've been working on. I've been taking the provincial biomass availability data and working to model on a high level how much CO2 can be removed from BECCS across the nation, not just focusing on electricity, but other technology options and biomass feedstocks as well. So starting with wheat straw and forestry residues as the biomass, I've factored key things like the residue availability, any losses in the residue from transportation, et cetera, and of course, the key ingredient, which is the carbon content of the biomass. And in this image here, I'm showing just a snippet of my early findings. On the y-axis, we have kilotons of CO2 removed, and the lines represent the CO2 removal from different provinces, depending on the availability of the biomass. And I'll just highlight that orange line there on the top. We can see that this correlates perfectly with Emily's work that I showed earlier of where the forestry biomass is located. So in wrapping up, hopefully we have a good context, very, very quick, but good context of what BECCS is, how the technology works, and how it shows up consistently as a key part of our net zero toolbox. And as we've seen, there's still some really important questions to answer around sustainability in the Canadian context. But I've shared the work that our research group is doing to answer these questions and hopefully provide key insights to advance Canada's climate targets through BECCS. So thank you very much.